Ας αρχίσουμε λοιπόν τώρα τη δεύτερη διάλεξη. Είμαστε ακόμα σε εισαγωγικό στάδιο. Θα πούμε μερικά πράγματα. Better I will switch to English since we have some people in the audience that who cannot speak Greek. So today we will say a few things about statistical methods. But first let's start with some definitions. Maybe the definitions will seem to be irrelevant to the whole class in the beginning, but I guess at the end of the class you will understand why they are relevant. Okay, so let's start by defining a random experiment. So a random experiment is any process with uncertain outcomes, which means that the outcome of this process cannot be predefined, cannot be defined before we actually do the experiment or before this process will finish. For example, when we roll a die, when we roll it, we cannot predict the experiment exactly. It might be a number between 1 to 6, but we cannot say a priori what this number will be. Or flipping a coin or measuring someone's height. Before we see the person, so if we say, okay, I will measure someone's height, and we cannot say in the beginning that this person will be 170 or 160 or so on. And when we sample gene expressions, we cannot say before the measurement taken that the gene expression will be 70. So a random experiment actually is a random process. It's a process with uncertain outcomes. And in order to know the result, this random process must finish, must come to an end, and only then we can know the actual measurement. So, relative to the concept of random experiment is the concept of random variable. And a random variable takes each possible outcome of the experiment and assigns a numerical value to that outcome. So for example, a coin, if we flip a coin, the plausible values are head or tail, and we might assign the value of 0 and value 0 to head and value 1 to tail, and then this is a random variable. Or we may assign to head the -1 and to tail the 1, and again this is a random variable that takes the values -1 and 1, or takes the value 0 and 1 here. In this case, that the random variable accepts only finite values, we say that it is a discrete random variable. In other cases, when we measure, for example, the gene expression level, we have a gene 1, that takes some values, or that it might take actually some values, 4.29, 3.17, 1.1, 1.2, 1.3, and so on. It can take actually infinite number of values, or it can take continuous values. The same is true for gene 2, for gene 3, and so on. In this case, we say that the random variable is a continuous random variable. So some observations, like when we flip a coin, or when we measure the expression level of a gene, or when we measure the height of an individual or the weight of an individual, again we say that this is a result of a random process or of an experiment that we cannot predefine the outcome. So in these cases, statistics is useful. But let's see why it's useful. And I think the best text that I found to describe what's happening with statistics is actually from the guy who defined all these terms and actually gave the foundations of modern day statistics. And this is this guy is called Fisher. So he wrote a paper, a long one, about 100 years ago, and he defined the purpose of statistical methods. And it's very interesting to read this. He writes, in order to arrive at a distinct formulation of statistical problems, it is necessary to define the task which the statistician sets himself. So, now starts the interesting part. Briefly, and in its most concrete form, the object of statistical methods is the reduction of data. This is very, very interesting. And very unusual, actually. So what Fisher says here is that the goal of the statistical methods is to reduce the data. Somehow not to have so much data. Or to represent the data with fewer values. And he explains that a bit further, and he says, a quantity of data which usually by its mere bulk is incapable of entering the mind is to be replaced by relatively few quantities which shall adequately represent the whole, or which, in other words, shall contain as much as possible, ideally the whole, of the relevant information contained in the original data. So Fisher says here that my goal as a statistician is to reduce the data. And he explains that, and he says, if we have a lot of data, a quantity of data, which is a lot and maybe too much for us to understand, then by using statistics, we will replace this amount of data with relatively few quantities. And these few quantities will have a very interesting property. These few quantities will adequately represent the whole. All the information, that's what he means. Or, in other words, they will contain as much as possible from the whole, or ideally the whole, of the relevant information contained in the original data. So he explains here what is the goal, what is his goal as a statistician to have. So by observations we have a lot of information. Somehow we compress this information and we represent it by a few numbers, a few quantities, as he says here. That these quantities, however, they will contain ideally the whole or as much information as possible that these observations had. And in the next paragraph here, he writes how to accomplish that. And it's a very interesting idea. This object is accomplished by constructing a hypothetical infinite population. We'll explain this a little bit further, of which the actual data are regarded as constituting a random sample. The law of distribution of this hypothetical population is specified by relatively few parameters, which are sufficient to describe it exhaustively in respect of all quantities under discussion. Any information given by the sample which is of use in estimating the values of these parameters is relevant information. We'll continue that later, but let's see the first few lines. So in the first paragraph he said what is his goal, to somehow to compress the information of a lot of data with a few quantities, and then he says how to do that. He says, we can accomplish this by constructing a hypothetical infinite population. And this sounds a bit strange here, because we have a lot of data, we're going to compress them, and we will achieve that by constructing a hypothetical infinite population. And the key and how to actually achieve that is here. This infinite population, however, what we believe for this infinite population is that the data that we observed is a random sample from this infinite population. So our sample here and the infinite population are connected. Because this random sample is coming from an infinite population, theoretical infinite, hypothetical infinite. It doesn't exist actually in reality, this population. This sample is coming from this infinite hypothetical guy. So this is number one, very important, and number two actually is here. This hypothetical population is specified by relatively few parameters. So even though it's infinite, only a few parameters are necessary to describe it. So what we say here is that our sample, which comprises a lot of data, is coming from an infinite population, and this infinite population is described only by a few parameters. Which means that if we know these few parameters, in principle, we have all the information we have here. We need that this sample provides actually. So this is the whole idea here. We have a sample in order to learn something for the population, and to learn actually the few parameters that define the population. So I have made some notes here. Our goal is to reduce the data. We collect data. These are many values, and we are incapable to understand them actually. And then we want to summarize all these many values in few quantities that actually they will describe the whole. So from a sample, the collected data, we go to a population, which is this infinite thing, which is described by only a few parameters. In detail, we go from a sample to a distribution, and this distribution actually represents the population. So from a sample, which are these values here, we just go to a distribution which is described, for example, the normal distribution only by mean and the variance. And if from the sample we are capable to learn the mean and the variance, then actually we know all we need to know for this population. And Fisher, in the next few lines, says something more, that usually the data, the information that they contain, so he separates a few things here. He says that, okay, sometimes we need to learn just something from the population. For example, we need to know only the mean, or we need to know only the variance, or we need to know some other relative quantity. But the data might contain more information than that. So much of the information supplied by any actual sample is irrelevant. That's what he says here. So for example, if we are interested in the mean, the data contain information also for the mean and for the variance. We are not interested in the variance, so the data contain more information that we need to know actually. And he says here the goal of the statistician, it is the object of the statistical processes employed in the reduction of data to exclude this irrelevant information and to isolate the whole of the relevant information contained in the data. So our goal as people who are doing statistical analysis is actually to get from the data what we need to know in order to understand the population or what the parameters that we are interested in. And if we know the parameters that we are interested in, we know actually the population that gave rise to the sample. Thus, we know everything that we need to know. So this is the purpose of statistical methods. And it's one of the most beautiful texts that I have seen that connect the sample with the hypothetical infinite population. And when I say hypothetical, it's not a natural population, does not need to exist. It's actually a mathematical construction. But the data are coming from this mathematical construction, or we assume that they are coming from this mathematical construction. This mathematical construction is described by only a few parameters, and from the sample we will go to learn these few parameters, to learn the distribution, and therefore to learn the population. Okay, that's it. Thank you very much.